So now that we've taken a look at how to design and implement a Memoizer, let's see how we could apply this to the PrimeChecker app. And this actually goes back a number of probably months at this point, but there's been this app I've been using kind of as a running example for a lot of the different Java executive framework components. And we're going to see how we could apply the Memoizer to this PrimeChecker app. Remember, the PrimeChecker app basically goes ahead and checks to see if random numbers are prime. And we're going to use the FutureTask-based Memoizer as part of this process. Just a quick recap. Remember, this app is embarrassingly parallel, which means you can leverage lots of cores, lots of threads, and it's also compute bound. Computing a prime number is not something that blocks on I/O. Quick recap of the class itself. Main activity checks the primality of count random numbers using the executor completion service with a thread pool and the prime callable class. And so here's what it looks like. We go ahead and make ourselves a new fixed thread pool. In this particular case, we could of course do a cache thread pool or a work sharing, work stealing pool or whatever we wanted to, but we use a fixed thread pool for this particular use case. And we tune that to the number of processor cores, because after all, this is a compute bound operation, so why the heck not? And then we use a Memoizer in order to be able to actually perform the caching operation here. There's a method called prime callable. We've actually looked at this way back in the day. This, again, is like a month or so ago, maybe around that time, probably early to mid-March. And this implements the callable interface, which means it's got a call method. We'll take a look at that in a second. It's got a couple of fields here. It's got a prime candidate field and a PrimeChecker function. You can see that the function is passed in as a parameter, and the PrimeChecker is given the PrimeChecker, and that checks to see if the prime that's passed, it checks to see whether a number is a prime or not, and it gets stashed away in this field. And here's the hook method. So this is the hook method that makes a new prime result, where the prime result is going to store the prime candidate. That's the number we're checking for primality. And we're going to go ahead and apply the function on the PrimeChecker to see if the prime candidate is in fact prime. And this particular call will run in the context of some thread in the fixed size thread pool. What's cool about this, and this is really the genius of the way that we implemented our Memoizer, is Memoizer implements the functional interface. So this particular class here just thinks it's dealing with a function, as you can see here, but in fact we can pass to it a Memoizer. And so we can transparently optimize this call to apply by using a Memoizer. Now, under the hood, the prime result is actually a record. It's a Java 15 record, which is just sort of like it's like a class that doesn't contain all the other gobbledygook that classes have, such as a v-pointer or a monitor lock or monitor condition and all this good stuff. It just basically contains fields. In this case, the fields are the prime candidate and the result of doing the prime computation. Here's what the code looks like to set up and initialize and run the computations here. We start out by making ourselves a new Memoizer, and that caches prime results. So going back to a question we asked about earlier, computing whether a number is prime, especially a big number, takes a while. So we're going to use the Memoizer so that if you've already computed the same number, then it'll look it up and come back much quicker. So that's the good part about that. In this particular case, we're just going to use a brute force checker, but it's trivial to change that to a smarter checker, like a sieve of Arachnios or whatever it is, that would be smarter about doing the checking. So we can parameterize through behavior parameterization the actual computation to do the prime number checking. So you could go from this to this with just a change in the code, but no changes to the classes, just the change to the way you initialize it. We then have a little Java stream where we generate count random numbers between this lower bound and this upper bound, and I intentionally make them fairly close so we'll end up generating duplicates. And then for each of those values, we turn them into calls to the prime callable constructor, passing in the number and the memoizer, which we set up here. Notice that this thinks it's getting a function, but in fact, it's getting a memoizer, and that works because a memoizer is a function. And therefore, we can use this wherever we expect to have a function used, because it keeps track of this function. And then what we do, because we're using the executor completion service, is we go ahead and we submit the prime callable, each of these prime callables, to the executor completion service, which goes ahead and does the computations in some thread in that fixed size thread pool that we use to initialize everything to begin with. And notice that there's no need in this case to have a list of futures because we're using the executor completion service. So the executor completion service, as you may recall from earlier lessons, keeps track of its own completion queue and therefore is much cleaner. Here's the rest of the program. The key parts: we create ourselves a thread called create a completion runnable, or rather we make a runnable, and then we go ahead and we make a new thread that's passed the completion runnable as it's runnable, so it'll go ahead and do the computation there, and then we go ahead and start that particular thread. So it's off to the races, running in the background, doing its thing. Here's the completion runnable class. It implements runnable, and it's got a run method, and what the run method does, this actually should look very familiar to what you guys did for assignment 3A, where you just have a loop that iterates for the number of operations that you set out, which in this case is a number of random numbers you're checking for primality. And for each one, we call take, followed by get. Remember, get doesn't block, but take may block if there's nothing in the completion queue yet. So take will block till it's got something to work with in whatever order it happens to occur. And then get is going to get the result. That stores it in the prime result. And then we go ahead and print the results out. Remember, that's running in the background. Little Androidism here. We use this class called retain state to keep track of all the concurrency objects that need to be retained across runtime reconfigurations. Remember, in Android, if you have your phone in portrait mode and you rotate it to landscape mode, that triggers what's called a runtime reconfiguration. And that shuts the current activity down and then makes a new activity that's running in the different layout, either portrait or landscape. But we want all these computations to continue running in the background. So we plop this stuff, we put all the concurrency-related fields or concurrency-related objects into this class with a bunch of fields. And then we use a very clever hack in Android called get last non-configuration instance and on retain non-configuration instance. And I won't bore you at the moment with all the details. If you want to read about that, you can read about it here. There's other ways of doing this in Android now, but this is a particularly easy way of doing it, and it works in old versions of Android too. Okay, so that's the end of our overview that talks about how to apply the Java future-based Memoizer to the PrimeChecker app.